Hello, today we're going to be graphing exponential functions. So in the past we have graphed linear functions and those ones look like a straight line. Exponential functions are going to look like something completely different. So let's take a look at what actually is an exponential function. So looking at these two problems here, you notice that both of them have a base that is being raised to an x power. When the x is the exponent, it's an exponential function. To identify what the graph should look like, what we're going to do is we're going to plug in all of these different x values you see in the table for your exponent, and we're going to evaluate. So 2 to the negative second becomes 1 over 2 squared, which becomes 1 over 4 for your y value. For the next one, you're doing 2 to the negative first power. We're just plugging x in. That becomes 1 over 2 to the first power, or 1/2. 2 to the 0 power is 1. 2 to the first power is 2. And 2 to the second power is 4. Once we've plugged all of those in, we can go ahead and start graphing them. So negative 2 comma 1/4, negative 1 1/2, 0 1, 1 2, and 2 comma 4. This graph right here represents an exponential function. Notice it does look different than our linear functions. Instead of looking like a straight line, this kind of looks like a slide, if you will. So when we look at this here, our domain from left to right, our graph has arrows on both ends, so it's going to be negative infinity to positive infinity. Your range is going to go from low to high. This graph looks like it touches 0, but in actuality, let's go ahead and draw a dotted line across at 0. Our graph would actually never get to 0. If you keep on plugging in more and more negative numbers, you get smaller and smaller fractions, but you'll never get 0. So here for our range, we're going to use a parentheses to show that our graph doesn't actually touch 0, but it does go up for forever. So it's from 0 to infinity. And then we'll wait for a moment for that next exponential part. Okay, so that is 1a. What we're going to do is we're going to pause on 1b and we're going to move down to 1c. We're going to look at this exponential graph. We have 1/2 as our base. So what we're going to do is just like the last one, we're going to plug in all of our exponents up for x. So we're doing 1/2 to the negative second power, which is actually 1 to the negative second and 2 to the negative second, which we can't have those negative exponents, so it becomes 2 squared over 1 squared, which in essence is 4. If we do 1/2 to the negative first power, that's going to become 1 over 2 to the negative first power, which is 2 to the first power, or 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 to the second power is 1 squared over 2 squared, or 1/4. So now if we take those and graph those as coordinate points, you get negative 2 comma 4. You get negative 1 comma 2, 0 comma 1, 1 1/2, and 2 1/4. And you can connect these and see that this also looks like that exponential function, but it's kind of going that other direction. I'm also going to go ahead and draw in this dotted line horizontally, kind of showing that my graph is going to get closer and closer and closer to that, but never actually touching it. So for this one, you have arrows on both sides there, meaning your domain is from negative infinity to positive infinity. Range is low to high, so this graph gets down to 0, but it doesn't actually ever touch 0, so I use parentheses. And this graph goes up for forever. And we're going to wait on that exponential part right after that. And so looking at all of this, you can see our first two examples, and then you can see B and D are going to be very similar to it with just different bases. So I'd like you to go ahead and try B and D by plugging in those x values and figuring out your y values. If you need to work with someone near you, that's fine. But go ahead and figure out your table of values and your domain and range for both of those. And then after you've done that, you can play again, and then we'll kind of talk through it after that. So pause the video, try those, and then come back to the video once you're done. Okay, let's go ahead and take a look at B now that you've plugged in your x values. We should get our y values to be 1 over 9, 1 over 3, 1, 3, and 9. And you can see your graph here starts low and increases for forever. Your domain is negative infinity to positive infinity, and your range is 0 to infinity. And let's check out D here. If you have the negative second exponent, you end up getting 16 because you have to flip your fraction and then square it. Negative 1 for your exponent would be 4, then 1, 1/4, and 1/16, and you can see that shape of that graph there is the slide, making this exponential. So if we kind of zoom out to look at the scope here, these are what exponential functions look like. So exponential functions can go up for forever or they can go down for forever, and it's all dependent on what the base of the problem is. The first two here, we're going to classify those as exponential growth. Exponential growth is when you start low and you end high. If your base, aka whatever is being raised to the x, if your base is greater than 1, then you're going to have growth. So if you had 5 to the x or 1.5 to the x, all of those would be growth. Whereas you can see examples C and D here. Those ones start high and end low. That is exponential decay. So if your base, again, whatever is being raised to the x power, is a fraction or decimal in between 0 and 1, that is going to end up being decay. So if you had 1/5 to the x or 0.75 to the x, those would be decay because your bases would be less than 1. One thing you'll notice is that all 4 of these graphs have those dotted line going across the side. That is something called an asymptote. Now this word right here looks a little weird, but it's called an asymptote. An asymptote is going to be on a graph. It looks like a dotted line horizontally. It is a line that the graph approaches but never touches. It's a graph the line approaches but never touches. So every exponential function is going to have an asymptote on your graph. So what we're going to do is we are now going to start taking these exponential functions and then moving them all around, just like we did with our absolute value graphs. So with our absolute value graphs, we learned that the a value out in front is a vertical stretch or a vertical compression if it is greater than 1 or less than 1. So for instance, we don't know necessarily what our base is yet, but if there's a 3 out in front, that means it's a stretch. If there's a 1/2 out in front, that means it is a vertical compression. If there's nothing out in front, that just means your a value is 1 and it's neither stretching nor compressing. If your a value is negative, then it's going to reflect over the x-axis. So if you have like a -2 out in front, that's going to reflect and then also stretch. Your h is up there with the x value, and that's going to move your graph left or right. So if you, for instance, have x plus 3, that would move your graph left 3. Or if you had x minus some number, that would move your graph right, whatever that number is. So it always does the opposite of what you think it should. Your k value is at the end. That's going to move your graph up or down. So for instance, if you had some exponential function that was plus some number, that's going to move it up. If you had something that is minus some number, that is going to move it down, however much that was. Now your base is going to be important here. So we have an extra value. It is this b value. B is your base. And it's always important to identify your base, because our base is going to tell us what table of values to use with our equation. So I want you to think about your x and your y values. We don't want to necessarily have to recreate a table for every graph, but we're going to have to a little bit, but depending on what that base is. So the x values that you're going to have to know are going to be -1, 0, and 1. Those are normally what we plug in for our x values when we're creating our table. For your y values, the ones that you're going to have to know are dependent on whatever your base is. Your y value is going to be 1 over the base, 1, and the base. So this table of values is going to be something, again, you have to know this, you have to memorize this, because this is how we're going to start moving our graphs all around. So we'll show a couple of examples of that coming up here. So some other key things to know here are your asymptote is always going to be y equals some number, because it is going to be a horizontal line that you see on the graph. And it's always specifically going to be whatever your k value is. When you start shifting left and right and up and down, you're going to steal your k value. That's your asymptote. For all exponential functions, your domain is -infinity to +infinity. Your range depends on the graph. So you always have to graph it first and then identify your range. It's either going to be some number to infinity, or it's going to be -infinity to some number, depending on how your graph looks like. Your graph is going to be exponential growth if it increases from left to right. So if your base is greater than 1, that's growth. It's going to be decay if it decreases from left to right. So if your base is in between 0 and 1, it would be decay. And one quirky thing to note here is that it will be neither growth nor decay if your A value is negative. If your A value is negative, your graph gets flipped over, and so it doesn't look like growth or decay. It looks like the opposite of what it should be. So this is basically just a whole lot of information. Let's go ahead and see a couple of examples to see what all this means. So let's go ahead and take a look at this example here. We have y equals 5 to the x. So the first thing to note is that 5 right here is a really important thing. This is your base. So if it's your base, it is not your a, h, or k value. So your a is normally out in front. There's nothing there, so it's a 1. Your h is normally with the x. There's nothing there, so it's 0. And your k is normally afterwards, and there's nothing there, so it's also 0. The table of values was the one that we had up here that we have to memorize. Your x values are -1, 0, and 1. Your y values were 1 over the base, 1, and the base. And in this case, the base is 5. So your y values are 1 over 5, 1, and 5. Now that might seem kind of weird, but if you think about plugging in these x values here, 5 to the -1st power is 1 over 5. That's where we're getting that. So what we're going to do is we're going to graph all of these points. So -1, 1/5, 0, 1, and 1, 5. This is what this graph would look like. The asymptote would be y equals 0 because we're not moving up and down at all. This is exponential growth because our base was 5 and we didn't get flipped over. Your domain is -infinity to +infinity. And your range starts at 0 and goes up for forever. Okay, so that's it for this video. We'll do one more. If you come back for the next video, it'll be short, and we'll do example 3, which now start throwing in your shifts left and right. Thanks for listening.